Students, this is the first topic, that is transformer EMF or stationary loop in time varying magnetic field. Consider a stationary loop of resistance R here, of resistance R, okay, and there is a time varying magnetic field. Here, let us assume that there is a time varying magnetic field. This time varying magnetic field is going to create a magnetic field with this coil, that means magnetic flux through this coil. Okay, if you are going to move nearer to the coil, the magnetic field is going to be increased. If we are moving away from the coil, the magnetic field is going to be reduced. That's why I am writing here in this manner. It is an increasing magnetic field with respect to time. The resistance is R, then there is an induced current here, then there is an electric field. This is induced magnetic field. Okay, that's why the figure name, if you observe that, induced EMF due to a stationary loop in a time varying magnetic field. This is the first concept, transformer EMF or stationary loop in a time varying magnetic field. Now we know that according to Faraday's law, we know that the induced EMF is equal to minus N into d phi by dt. Let us consider this closed circuit or this coil consists of only 1 turn. That means if N is equal to 1, then V EMF is equal to minus d phi by dt. We know that phi is equal to, that means magnetic flux is equal to surface integral of b bar dot ds. Okay, then I am going to write this induced EMF in terms of the electric field and magnetic field. Now observe that the induced EMF is equal to closed line integral E bar dot dl bar is equal to minus, observe that, minus this phi becomes surface integral minus surface integral, this differentiation d by d dt, I am going to write dou b bar by dou t bar dot ds bar. Don't be confused why I have taken the partial differentiation. Why? Because we know that from the starting of this subject we are going to consider the partial differentiation. Now this is a very interesting point here. Why the induced EMF is equal to the closed line integral of E bar dot dl bar. Actually it is a closed path of length L, closed path of length L, the electric field. Okay, here I am going to consider closed line integral of E bar dot dl bar. From the second unit, from the first unit, we know that in the first unit this E bar dot dl bar, that means the closed line integral of E bar dot dl bar is equal to 0 due to the conservative nature of electrostatics. Okay, why? Because in the static electric field, if you want to move a charge from one point to another point, the work done is equal to 0, because at the first point the potential and the second point the potential both are same, therefore the potential difference will be 0. Now here the potential difference is not 0 because it is not a static electric field, it is a time varying electric field. Because of this time varying electric field, okay, we have a different potentials, therefore we have a definite potential difference. Therefore the potential difference, that means the induced EMF is equal to the closed line integral of E bar dot dl bar, which is equal to, if you observe that, okay, according to Faraday's law, which is equal to minus surface integral of dou b bar by dou t dot ds bar. This is the first Maxwell's equations in time varying field in integral form. Let us assume that it is expression number 1. This EMF induced by this time varying current or by this time varying magnetic field is referred to as transformed EMF. Okay, actually in power analysis due to the transformer action. Why I am calling it as a transformer action means, okay, I am going to consider, okay, a coil here. I am going to consider a coil here. Sorry, not like that. I am going to consider a coil here with some battery and some switch. Sorry guys, some battery and some switch and a coil here. Okay, see, because of this is a primary winding, this is a secondary winding. Due to the transformer action here, this induced EMF we are going to call it as a transformer EMF. Are you clear? Transformer EMF. Okay, by applying the Stokes theorem to the middle term of this equation 1, okay, we know that the Stokes theorem is nothing but this closed line integral is going to be open surface integral of this. Closed line integral of E bar dot dl bar is equal to open surface integral of curl of this electric field. Then this expression 1 is going to be written as, okay, this induced EMF is equal to, okay, surface integral of curl of electric field dot ds bar is equal to minus surface integral of dou b bar by dou t dot ds bar. Is it clear? By equating these two, we have the curl of electric field is equal to minus dou b bar by dou t. Okay, this is one of the Maxwell's equations for time varying field in differential or point form. Now the equation 1 is the Maxwell's equations for time varying field in an integral form. That means this I am going to call, this is the Maxwell's equations in time varying field in integral form. This is the Maxwell's equations in time varying field in a point form or differential form. Okay, previously in the first unit it is equal to 0, but in the time varying field it is not equal to 0. It is the rate of change of magnetic flux density. Okay, now coming back to the second concept, in this case we are moving a loop. That means the loop is a time varying. We are keeping here the magnetic field as a static magnetic field. This EMF we are going to call it as a motional EMF. Okay, when according to Faraday's law, once again, when a conducting loop or when a coil or when a closed circuit is moving in a static magnetic field, an EMF is induced in the loop. Okay, that's why since the magnetic field is static, we are going to consider the force on a charge which is moving with a velocity u bar in a magnetic field. This magnetic field is a static. Now we know that the magnetic force or the motional force is equal to q, the velocity, cross the magnetic field intensity. Now we define the motional electric field here. We know that electric field is equal to force upon charge. Therefore force upon charge is equal to the cross product of the velocity of the charge and the static magnetic field. Therefore according to Faraday's law, the induced EMF, the EMF induced in the loop is V EMF is equal to closed line integral of motional electric field is equal to the closed line integral of, since EM bar is equal to U bar cross B bar, this becomes the EMF which is known as motional EMF, or it is also called as flux cutting EMF. Flux cutting EMF. Why? Because here you are not moving your magnetic field, you are keeping your magnetic field as a static one and you are moving your coil nearer or away from the magnet. Okay, that's why the flux is going to be cut. This is known as flux cutting EMF because it is due to motional action. Now coming back to the third case, time varying loop, or if you observe that time varying loop, or you can also call it as moving loop in a time varying magnetic field. Now in this case both transformer EMF and motional EMF are present. Therefore the total EMF is given by the total induced EMF is given by closed line integral E bar dot dl bar is equal to, it is the EMF due to the first case transformer EMF, it is the motional EMF, both the EMFs are present. Now by applying the Stokes theorem to this term and to this term, it becomes like this. Then it becomes curl of electric field is equal to, already it is a surface integral, therefore it is going to be cancelled, dou b bar by dou t plus here del bar cross this term, del bar cross u bar cross b bar by Stokes theorem. This is known as the three cases. Okay, the first case is stationary loop in a time varying magnetic field. The second case is, okay, moving loop or time varying loop in a static magnetic field, or the third case is time varying loop in a time varying magnetic field. This completes the transformer EMF and motional EMF. Now we are going to see a very important topic, that is inconsistency of Amperes circuit law and displacement current density. Okay, we will see what is the inconsistency in Ampere's circuit law, how it is rectified by Maxwell's. Now we will see once again what is meant by displacement current density. Now observe that we are going to consider the first step, Ampere's circuit law. Okay, the basic Ampere's circuit law in a point form. We know that the curl of the magnetic field intensity is equal to the current density. Okay, taking divergence on both sides, by taking the divergence on both sides, according to the vector identity, we know that the divergence of the curl of any vector field, the divergence of the curl of any vector field is 0. That means this del bar dot j bar must be equal to 0. But this result is not consistent with the continuity equation. Why? Because here it is a time varying field, it is not a static field, therefore this result is not consistent with the continuity equation. Why? Because we know that the continuity equation states that the divergence of current density is equal to, okay, rate of change of volume charge density. Therefore I can say that by the continuity equation, del bar dot j bar is equal to minus dou rho v by dou t, which is not equal to 0. This indicates that Ampere's circuit law is not consistent. That means it is inconsistent for time varying conditions. So Maxwell's done a modifications. So a modification is required for Ampere's law. To this modification, Maxwell's add a term, that is JD bar. We will see later what is meant by JD bar. It is actually displacement current density. We will see later. Okay, Maxwell's add a term JD bar in this equation 1. Then del bar cross H bar becomes J bar plus JD bar. Now once again taking divergence on both sides. Observe that the divergence of del bar cross H bar, now it becomes divergence of J bar plus divergence of JD bar. This J is conduction current density, this is displacement current density. Now according to the vector identity rule, this becomes what? 0. Then divergence of J bar plus divergence of JD bar becomes 0. Then divergence of JD bar is equal to minus divergence of J bar. It is not JD, J bar. Then we know that divergence of J bar, this is JD itself. We know that divergence of J bar is equal to minus dou rho v by dou t. Then minus of minus becomes plus. Then divergence of JD bar is equal to dou rho v by dou t. Now we know that from the Gauss's law in point form, we know that the divergence of electric flux density is equal to volume charge density. Now I am going to substitute, okay, this expression in this. Then it becomes divergence of JD bar is equal to dou by dou t of del bar dot d bar. Then this curl I am going to take, this del operator I am going to take outside. Then it becomes dou d bar by dou t. By comparing these two, I can say that JD bar is equal to dou d bar by dou t. This is known as displacement current density. Displacement current density is equal to rate of change of electric flux density. Okay, now with this expression I can also say that the displacement current is equal to surface integral of JD bar ds bar. This is the displacement current. Is it clear? Okay, but this is known as displacement current density. JD bar is equal to dou d bar by dou t bar, and we know that J bar is the conduction current density. This is from Ohm's law. Okay, then finally the modifications of Ampere's circuit law is del bar cross H bar is equal to J bar plus JD bar, in no sense dou d bar by dou t. This is point form or differential form of one of the Maxwell's equations, okay, for a time varying field. Okay, if you want to write this in an integral form, okay, now I am going to write from once again from Stokes theorem here. Okay, I am going to write directly here. This becomes the closed line integral of H bar dot dl bar, which is equal to, observe this here, it becomes the surface integral J bar plus dou d bar by dou t dot ds bar. This is an integral form. This is the Maxwell's equations for time varying field. Okay, or you can also say that it is the modified Amperes circuit law. Modified Amperes circuit law. Is it clear, all of you? This is modified Amperes circuit law. Okay, this is the inconsistency of Amperes circuit law and how Maxwell's modified this expression. Now we are going to prove that. Okay, whether the displacement current and the conduction current both are equal or not. Now this is very important question. We are going to prove that the current enclosed by the Ampere loop is equal to the conduction current or it is equal to the displacement current. We are going to prove that this conduction current and this displacement current both are equal. Okay, to prove this concept I am going to consider this circuit. Observe very carefully, guys. Consider a circuit with a AC supply here. This is an AC supply, okay, and this is a capacitor here, and I am going to consider two surfaces, S1 surface and S2 surface. Is it clear? Now I can able to take an Amperian loop here. Okay, in surface 1, applying an unmodified form of Ampere's circuit law to a surface 1. Okay, as shown in figure. Now we know that the closed line integral of h bar dot dl bar is equal to the current enclosed. Okay, in the surface 1, j bar dot ds bar is equal to what is the current flowing? Okay, it is a conduction current. Why? Because it is a conductor. The current flowing through this is a conduction current, where I is the conduction current because it is passing through the conductor. Now applying an unmodified form of Ampere's circuit law to a surface S2. Let us assume that here there is an Amperian path here in an insulator. Okay, this is surface 2 shown in figure. Then closed line integral of h bar dot dl bar is equal to S2. Surface integral of j bar dot ds bar is equal to I enclosed. If you observe from this figure, there is no conduction current. Since there is no conductor here, therefore there is no conduction current. Okay, therefore the current enclosed is equal to 0. Is it clear? Okay, because no conduction current flows through it. Therefore, but we know that this is a closed circuit. Whatever may be the current present here, the same current should be present here. Are you clear? And the same current should be present here since it is the closed circuit. Is it clear? Therefore, what is the current present here? Faraday's placed a magnetic field here, magnetic needle here, and he observed that this magnetic needle is going to be moved. Okay, and he also placed the magnetic needle here. It is also moving like this. That means he concluded that whatever may be the current flowing here, the same current is going to be flow here. For that purpose, he modified the Ampere's circuit law. Therefore, Ampere's circuit law is modified and a displacement current is included. That means closed line integral h bar dot dl bar is equal to such S2. That means in the surface 2, we have a displacement current density jd bar dot ds bar. Okay, since we know that jd bar is equal to dou d bar by dou t, okay, dot ds bar, then this dou by dou t I have taken outside. Now I know that surface integral of d bar dot ds bar can able to write as the charge. Is it clear? Therefore I am going to consider this, okay, as charge dou q by dou t. In a sense, rate of change of charge is nothing but current. That means from that it is clear that, so we obtain that same current for either surface. That means surface 1 and surface 2, for either surface the same current is going to be flow. Although it is a conduction current in S1 and a displacement current in S2, both the currents are same. Therefore, hence it is proved. Finally, we are going to conclude that, okay, in S1 surface displacement current is 0, but in S2 surface conduction current is 0, but both the currents are same. That means what I am trying to say here is, at this surface there is no conduction current, there is no displacement current, only the conduction current is present. At this surface there is no conduction current, only the displacement current is present. That means we can prove that the current enclosed by the Amperian loop is equal to the conduction current, which is same as the displacement current. Is it clear? This is the topic of inconsistency of Amperes law and displacement current density. In the next topic we will see the Maxwell's equation. That is the final video for this unit number 3 except the last topic. Okay, thank you very much.